So we're going to talk about the discovery of excited universe using the supernova data. Supernovae are rare events in the galaxy. Uh, the last time a supernova exploded in our Milky Way was about 400 years ago. So how are you going to, uh, you can't wait that long to find a supernova to do your observation. However, using new technology, large mosaic CCD charge coupled device cameras, astronomers overcame this problem by simultaneously monitoring thousands of galaxies so that on average some 10 to 20 supernova can be observed in a year. By 1998, two collaborations, the Supernova Cosmology Project led by Saul Perlmutter and the High Z Supernova Search Team led by Adam Rees and Brian Schmidt, each had accumulated something like 50 supernova 1A at a high redshift, uh, greater than uh, 0.4. Um, and their corresponding light emitted at a cosmic time some 5 to 8 billion years ago. Okay. And they made the astonishing discovery that the expansion of the universe was actually accelerating, as indicated by the fact that measured luminosity were on the average like 20% less than anticipated. Remember, we said in accelerating universe, an observer light source would be dimmer than expected. And so basically find the Hubble curve actually bent upwards. The curve from the discovery paper. Uh, the Hubble plot, which is a function of luminosity distance versus redshift, okay, uh, lies above the matter-dominated curve. It was, you can see that the dashed curves are for the matter-dominated, which uh, uh, was omega m equal 0.3, and there's no cosmological constant. And the solid curves are the best fit of the observational data. Okay. Now it's hard to see from the first panel, but the vertical axis represents the distance modulus, which is directly related to the mass distance. Anyway, in the lower panel, the difference of uh, uh, the distance between the measured distance and the measure, which means the solid curve, and the expected value for decelerating universe, which is a dashed curve. So the data point basically lies above this, so the best fit is the solid curve. Okay. Now, it doesn't look very impressive, but you have to remember we're talking about measuring uh, light that's emitted 8 billion years ago. Uh, so that's really still amazing. They could do that. So from this, we can extract the energy component for matter and for dark energy, because the Hubble curve uh, traces distance as a function of the uh, redshift. So when the matter density tends to bend downwards and the dark energy tends to bend upwards, so by fitting the Hubble curve, we can then extract the value of the mass component and dark energy component. So to order to do this, we must first express the luminosity distance in such a way that depends on the energy density explicit, because we want to extract energy density. From this, we can find dependence on z from density as a function of scale factor, uh, because scale factor is directly related to redshift. So therefore, if you can express the uh, the luminosity distance in terms scale density, and density in terms of scale factor, scale factor is redshift. So therefore, you can get the the density in terms of redshift. Anyway, we can see how it works out. The proper distance, or the co-moving distance from the light emitting light entry in the light interval here. Okay, here's invariant interval for light is equal to 0, and minus c squared dt squared a squared, the distance, covariant moving distance. So therefore, the differential of the proper distance equals ct over a. We integrate, we get this expression for the proper distance from the from the emitting source to us. Because the Hubble constant is a dot over a dot is a different respect to time, we can replace the time integration variable by the scale factor, because this expression over dt, see dA dt over a is h, so therefore dt is equal to dA over a and h. And then by replacing the dA by the redshift, okay, because a and the redshift are directly related. So this expression here, we can replace the dt by dA prime over a prime square h. That's from this formula, and then replacing the dA by dz, dA over a square by dz. So therefore, dz just, and then there's a minus sign. In the meantime, we can replace the proper distance by the corresponding luminosity distance. Remember, all you need to do the proper distance is an extra 1 plus z factor. So therefore, the luminosity distance as a function z is this. But we're interested in expressing this dependency through the density parameter. So therefore, we have to replacing the Hubble constant in the denominator, okay, in terms of density. Remember, density scales like 1 over a cubed, and dark energy is constant. So, and also this came from a break exercise we did. That's another way of writing the first Freeman equation. Okay, just that h is a function of scale can be written as h now of the using this scaling formula for the densities. Then of course we can replace a by z. So this I'm just repeating what I said. So the luminosity is a function of z is in this integral, and in the denominator the Hubble constant. Hubble constant can be expressed at any redshift can be expressed in terms of density of now. Okay, because we know the scaling behavior of the density. Now here's a plot of the observation data as we extract the energy components, because observed upward band of the Hubble curve roughly fixed by omega lambda over omega m, because this set of data, this confidence level data, this green curve is basically omega lambda minus omega m, because omega lambda lifts up the curve while omega m bends it down. So there's difference determines the shape of the confidence level. And then also we're assuming that's compatible with CMB boomerang maximum of the fact the universe is flat, which means that a lambda plus a plus is equal to 1. So this straight. So that what drawing here, this is the best fit for omega m and omega lambda. Okay, which would come out to be, again, this is the old data, and now I code here more recent fits, and this is omega m is 0.3, lambda is about 0.7. Okay, so the astronomical observation led to the most remarkable conclusion that most energy in our universe now resides in this mysterious dark energy, which behaves like a cosmological constant. Okay, that's the big discovery. From this, we can calculate cosmic time. The age of an empty universe, remember we said is Hubble time, which is 14.46 giga years. The matter content will shorten it because we decelerate the expansion, and dark energy to lengthen it because accelerator will lengthen it. So given the value of omega m, then we can one to shorten, one to lengthen. So knowing that value, we can calculate what exactly the uh, cosmic age. In fact, if we could derive a more general result, the cosmic age at any scale factor a, okay, and and of course the age of our universe is now is means when a is equal to 1. Just like before, t is equal to integral dt, and dt can be just like the last slides we can express in terms the scale factor is dA over a h, and then h expressed in terms of the uh, density components, we get this. Okay, so this is the general expression for constant time for scale factor a. Okay, so now if you assume that within a spatial flat universe, which means the omega not equal to 1, which is made of omega lambda plus omega m. Okay, so which means that all means that this last factor, 1 minus omega naught, can be taken 0. So therefore, this integral is just dA over square root of omega m over a plus uh, omega a square, lambda, omega lambda a square. And that's a simple integral. You can look up the integration tables. You find this integral gives this the integration is this result. So that's the general expression of the cosmic time at the value a, okay, in units of Hubble time. Now we can first make a check should this formula does work. So let's consider something we know of. For a matter-dominated flat universe without a cosmological constant, remember we talked about in the chapter 9, that's for before we introduce there's no cosmological constant, but for a matter-dominated flat universe, which means omega naught is equal to omega m and is equal to 1. And in fact, there's no cosmological constant. So base setting a equal to 1, okay, and omega m equal to 1. So this 1, this 1, this, okay. So we have this. But what we want is there's no cosmological constant, so this should be 0. So we ask, take the limit of this getting to small approach 0. So of course this approach 0, this is just 1. And so for lambda of 1 plus a small quantity epsilon, or in case this square root of omega lambda is equal to the lambda factor, the log factor is just epsilon. So that just cancels the 1 in the denominator. It gets 2/3 of Hubble time. Okay, that's exactly the result we obtained previously. Okay, saying that a matter-dominated flat universe without cosmological constants should have age 2/3 Hubble time. So this formula works, and now apply to the case of our real universe with the matter components, lambda component, omega lambda component, and you plug in the numbers here, you find this cosmic time is 0.955 times Hubble time. You plug in Hubble time 14.5 GeV, gets 13.8 giga years. Okay. So that's age of our universe with this components, this dark energy and this matter components. This and this